So today we have a guest who came all the way from Israel to be with us, Dr. Bernard Attali. I just realized, I go quite often to Japan, and I told him it's a very long flight. And then the Japanese hosts are merciless because the first night, as I get there, they take me out to dinner. The next day, it's 7 o'clock. I have to already be there, listen to presentations all day long, and then around 5 o'clock give my own seminar. I just realized I'm doing exactly the same thing today. So anyway, Dr. Attali came from Israel, where he is a professor of Physiology and Pharmacology at the Sackler School of Medicine, which is the School of Medicine for the Tel Aviv University. Bernard received his Ph.D. from the Weizmann Institute of Science, also in Israel, and then spent 4 years doing research as a postdoctoral fellow in Nice, France. And after that, returned to Israel and became faculty at the University of Tel Aviv, where he is now. And he's done really beautiful research on the structure and function of ion channels, notably IKS, the slow delay rectifier potassium channels, and its 2 subunits, and how they interact together. And he'll tell us today about this channel from the structure and function perspective. So thanks for coming.
Thank you very much, John. Feel very well here, and very grateful for your hospitality. I feel home here. Okay. So today I will try to present you a few set of data showing some properties of the gated motion and the assembly modalities of this channel complex. As an introduction, as you know, the multi-subunit membrane protein like transporters, clamps, ion channels are functional only when the subunit assemble together. And the assembly modalities and the inter-subunit interaction play a fundamental role in determining the gating mode and the kind of conformational transition underlying the ion channel function. And for potassium channel, so for the potassium channel superfamily members, they have exploited different modes of protein-protein interaction to direct channel assembly. And for example, Sackler-like voltage-gated potassium channel assemble as tetramer. So for the alpha subunit, they assemble as tetramer via the N-terminal T1 tetramerization domain, which also serve as a docking platform of interaction with the accessory cytoplasmic beta subunit. Actually, the T1 tetramerization domain is also very important for gating, and it is located in the N-terminus of the Sackler channel. So the question is whether other voltage-gated potassium channels are using similar modular intracellular domain to drive the assembly and the assembly specificity. So in our lab, we're working on the KB7 potassium channel, or the KCN2 channel, which is a small and important family of voltage-gated potassium channels, which include 5 members. We have the KB7.1 of KCN2-1 up to KB7.5. So as you know, I will not offend you saying that the KB7.1 as alpha subunit is expressed in the heart, in inner ear, kidney, lung, pancreas, and we know that this subunit is very important because human mutation are leading to cardiac arrhythmia. And the other members of this family, KB7.2 to KB7.5, are expressed in the nervous system, central and peripheral nervous system. For example, the KB7.2, KB7.3 are encoding the very important neuronal M current, which is very important for modulating the neuronal excitability. And human mutation in this subunit lead to neonatal epilepsy or myokine. And finally, this isoform, the KB7.4, is expressed in the inner ear, in outer cell neuron, in the central auditory neuron, and human mutation are known to lead to deafness. So today I will present you the kind of assembly modalities and kind of gating properties of the cardiac IKS potassium channel, which is very important for the repolarization of the cardiac action potential. And we know that the heteromeric assembly of the Kv7.1 alpha subunit with the KCNE1 beta subunit is necessary to encode, generate the cardiac voltage-gated potassium current, the IKS current. So we are focusing on a domain which is quite of interesting, especially if we compare it with other voltage-gated potassium channels, so the Kv7.1 C-terminus. And we know that the C-terminus of Kv7.1 is relatively a long polypeptide. It's a multimodular structure comprising, in terms of secondary prediction, in terms of the prediction of the secondary structure, it includes domain of alpha helices and coil-coil domain that form important protein-protein interfaces. By the way, I should mention that the Kv7 family of potassium channels do not have a T1 tetramerization domain in the N-terminus. On the contrary, the assembly domain is located in the C-terminus. And for example, we have in the proximal domain of the C-terminus two helices, two alpha helices, helix A and helix B, which are kind of gating sensor module that binds calmodulin and which plays a very important role in the folding of the C-terminus and probably also trafficking and a bit of gating. We'll see it later in the results. And we have also a distal part of the C-terminus which includes actually two coil-coil structure, helix C and helix D, and we'll see that they direct the channel tetramerization of the alpha subunit and also are very important in defining the subunit specificity of assembly. Just to remind you that the Kv7.1 isoform, the cardiac isoform of this family, do not assemble with Kv7.2, Kv7.3, or Kv7.4. So there is kind of specificity in subunit assembly. So in my lecture, I will present three sets of data. First set that shows that calmodulin, the calmodulin binding domain, this kind of sensor module is very important for channel gating and folding. And I will illustrate my purpose by showing also the impact of long QT mutation on this function of calmodulin. Then I will present you some data showing the assembly modalities of the channel complex, both on the side of the tetramerization of the alpha subunit and also of the interaction of the alpha subunit and the beta subunit. And finally, I hope I will have enough time, I will show you some interesting feature of the gated motion of the two subunits when we are actually using FRET as a reporter method to analyze this gated motion of the two subunits. So, first of all, the calmodulin sensor module. Calmodulin is very important for the folding of the Kv7.1 C-terminus. So we observed this function when, for crystallization purposes, we wanted to produce, overexpress this C-terminus, so this whole C-terminus in bacteria. So, and we started to express this C-terminus, this C-terminus in bacteria. And when you express it in bacteria and you try to make a paste and produce and purify this protein, it's very difficult because everything goes into the inclusion bodies. So when you have this bacterial suspension and you centrifuge, all the protein goes to the pellet. We have almost nothing in the supernatant, so you cannot, of course, purify and analyze this protein because it's not a soluble protein. However, if you co-express in bacteria the C-terminus of this alpha subunit of Kv7.1 together with calmodulin, then you get a soluble protein that you can purify and analyze. Not only calmodulin is important for getting a soluble protein, a properly folded protein, but the binding of calmodulin to the binding site of calmodulin, so these two helices, is important because if you remove the binding domain of calmodulin, so if you delete helix A and B, again, you try to co-express calmodulin together with this shorter polypeptide, okay, all these parts, everything goes again into the palate. So you have inclusion bodies, the protein is not properly formed. So now, illustrating this very important role of calmodulin binding to this proximal part of the C-terminus into helix A and B, I illustrate my purpose by showing the impact of long QT mutation, which are clustered. Some of the long QT mutation are clustered within helix A and at the boundary of what we thought helix A. I will show you later, actually, crystal structure data showing that actually helix A is much longer than what we expected according to the algorithm of the predicted secondary structure. So we have actually a very long alpha helix which actually connect, which is a prolongation of the S6 segment. It's a very long road, alpha helical road, that is actually representing this helix A. So what is the impact of this long QT mutation? We analyzed a few of them, of course not all of them, and we first checked what is the binding, what is the affinity of calmodulin for these long QT mutants, which are located, again, around within the helix A at this position, the boundary of what we thought the predicted helix A. And if we compare the binding of calmodulin using an assay, which is a calmodulin pull-down binding assay, and we quantify that. So if you compare with the wild type, you can see that in this pull down, all of these mutants, and we compared also a kind of a polymorphism, a very mild polymorphism mutation. So the long QT mutation bound much weaker calmodulin. So we have a much weaker binding of calmodulin to this long QT mutant located at this region of helix A. And these are the statistical data, and we have a weaker binding of calmodulin, either in the presence of calcium or in the absence of calcium. Then, since we found that calmodulin is binding much weakly to this region, we suspected that because calmodulin is binding much more weakly to this region, maybe we have a folding problem and a trafficking problem. So to check that, we wanted to know whether this long QT mutation had a trafficking problem by checking using cell surface biotinylation assay, whether this long QT mutant trafficked much less efficiently to the plasma membrane. And using this assay, we could compare the wild type and this long QT mutation, and you can see that using this cell surface biotinylation assay, all these 4 long QT mutants are expressed much weakly compared to wild type at the cell surface. And this is our kind of control, which is a polymorphism of the channel. So this mutation is expressed at the plasma membrane like the wild type. So to conclude, we have, for this long QT mutation located at this region, weaker calmodulin interaction with this long QT mutant, a decreased cell surface expression suggesting a folding and trafficking problem. Now, we wanted to know what is the impact at the functional level. So we expressed this long QT mutation and the wild type in CHO cells and recorded the current in the whole cell configuration of the patch count technique. And we found that for these long QT mutants, we have actually 3 main changes compared to the wild type. First of all, we have much less current density. We have much lower expression of the current. These are the IV density current compared to the wild type. and you can see that for all long QT mutation, we have much lower density of the current. We have a right shift in the activation curve, as you can see here. So all these mutants are right shifted compared to the wild type, and we have expression of macroscopic inactivation. So we have a gating defect also for this long QT mutation, located in this region of calmodulin binding. Then we wanted to know what is the impact of the co-expression of the beta subunit. So the beta subunit does not change very much the phenotype. Again, we do see a lower calmodulin binding using this calmodulin agarose pull-down assay, weaker binding of calmodulin to this mutant compared to the wild type. Regarding the current, we have a change. Actually, KCNE1, the beta subunit, can rescue, in a way, the kinetics, this macroscopic inactivation. For example, look at this mutation. So this is the mutation, the mutant of the alpha subunit alone. And when you co-express with the beta subunit, you lose this macroscopic inactivation. You recover this slow activation typical of IKS, but we still get, for all these long QT mutants, much lower current density, which actually accounts for the long QT phenotype. So even when you co-express this alpha subunit mutant together with the beta subunit, you still get a lower current density. So we have lower repolarization, potassium repolarization curve. Then we, since calmodulin is binding to this proximal domain of the C-terminus, we wanted to know what is the consequences of intracellular calcium increase if we know that, knowing that calmodulin is binding there. So it was important for us to see what is the impact of calcium, of increasing free intracellular calcium on the current. To do that, we did inside-out micropatches both in oocytes and also in CHO cells in order to know what is the functional consequences of increasing intracellular calcium. And to our surprise, we found that this is the trace, the control trace. So we step from the holding potential of minus 100 to plus 60 millivolts, and we found that there is an increase in the amplitude of the current when you increase the intracellular free calcium. And you need a few tenths of nanomolar calcium concentration. So it's very, very sensitive to increase in intracellular free calcium. And actually what we found, we checked that also in the presence, and this shows that that expression. We checked the effect of increasing intracellular free calcium when we co-express the alpha subunit together with the beta subunit, and these are a typical trace, an IV curve, a trace of IV curve in the absence of calcium and in the presence of 35 nanomolar free calcium. So we do see an increase in the current amplitude, an acceleration of the activation kinetics, and the left shift in the activation curve. So, and you can titrate this left shift, and this is a huge sensitivity to change or increase in intracellular free calcium. In a way, this IKS current behave like, of course, like BK channel. So it's very sensitive to voltage, but also very sensitive to increase in intracellular free calcium. So just to summarize this part of the data, we show that actually in healthy individual, the normal calmodulin binding to the alpha subunit, to the C-terminus of the alpha subunit, the KD7.1, is very important for the correct channel folding and trafficking, and for conferring to the IKS some calcium sensitivity. Yeah.
The calcium, no, when you finish. Go ahead, finish your thought.
Just conferring calcium sensitivity, which apparently is very important for consolidating the repolarization reserve. And of course, maybe to prevent kind of alternance to really secure the action potential for proper repolarization and preventing, of course, arrhythmia.
With that
Yes.
calcium dependence, it's in the low tens of nanomolar range. That's, you're going to go right through that during
Yeah, we
during
saturate. That's
a
right.
beat, and so
That's right.
and you get such a big shift in the voltage dependence. Could it make an ITO? Could it make a transient K current dependent on the calcium?
I think that the saturation, the sensitivity to calcium is so strong that we get saturated very quickly. I mean, even in resting calcium level. So that's the. We are still very puzzled by this data, because apparently we are now doing a lot of experiment on that, because we don't know exactly what is the mechanism. We found that the channel is very sensitive to CAM kinase 2. So there is a process. All these experiments were done in the presence of potassium pyrophosphate. When you don't add potassium pyrophosphate, you lose this regulation. So apparently this is a phosphorylation, dephosphorylation process. But I should keep very careful, because we have to elaborate on that, but we have this calcium sensitivity for sure.
So I have a question about the inactivation like of your mutations.
Yes.
Does casein-1 prevent all those mutations from inactivation?
No, not all. We have one mutation. Actually the same position. This arginine 366P instead of W, which is also a long QT mutation. You cannot rescue actually the macroscopic inactivation. And even in the presence of casein-1, you still get macroscopic inactivation. So not all, but most of them, I mean, in this region, most of them can be rescued in terms of the kinetics, not in terms of current density.
So do you think that the phenomenon looks like the inactivation, right?
Yeah,
so
yeah.
Is it really inactivation, or is it some like a dynamic change of commodulin binding?
No, this is really inactivation. You can measure recovery from inactivation. No, this is really, to what extent it's, of course it's related to binding of commodulin.
Right.
I agree with you, but by which mechanism, I don't know. Okay. Then we were interested in trying to attack a very tough problem, trying to resolve the oligomeric state of the KB7.1 C-terminus. And some of the modules in these C-terminus, mainly trying to see what is the stoichiometry of calmodulin binding to helix A and B. So this is shown here, helix A and B. And also to try to know what is the oligomeric state of coil-coil helix C and helix D. Okay. So using heavy tools, but very precise tool of analytical ultracentrifugation, both sedimentation equilibrium and sedimentation velocity experiments, which are very much more precise than size exclusion chromatography. So we try to analyze this oligomeric state. And we found that the C-terminus, again, all of these experiments with the C-terminus were done in the presence of calmodulin. Without calmodulin, you cannot express and you cannot work with this protein. So you need calmodulin in order to get a soluble protein. So we found that the C-terminus, the whole C-terminus, complex with calmodulin, is an elongated, non-globular protein with a tetrameric stoichiometry. So you have 4 C-terminus of the 4 alpha subunits complex with 4 calmodulin. So we have a stoichiometry of 1 calmodulin bound to 1 C-terminus. And I will go to it later by showing you some data of the crystallographic data of calmodulin bound to this proximal domain of the C-terminus. So we analyzed also using size exclusion chromatography, and we found that if you remove helix C and D, so these 2 coil-coil domains, and you just run this proximal part of the C-terminus, which comprises helix A and B and calmodulin, so all this complex is a kind of homomer. So you have no oligomerization. You have 1 calmodulin bound to 1 proximal part, helix A and B, okay? And you have this data shown here. However, we did also other experiments showing that you can bind calmodulin, wild-type calmodulins, and you have, again, a tetrameric stoichiometry. You can also have the same stoichiometry, tetrameric stoichiometry, if you bind mutant calmodulin that does not bind calcium. So you may have binding of calmodulin mutant, which does not bind calcium, in exactly the same stoichiometry. Then we try to analyze the stoichiometry of the coil-coil LXD and LXC. And we try to dissect by using, of course, deletion mutants. And we found, for example, that if you remove LXD from the whole C-terminus, you get a dimeric stoichiometry. So you have a dimer. So actually, LXC encodes a dimerization function. Then, again, using the analytical ultracentrifugation, so if you analyze LXD, LXD encodes a tetrameric function. Okay, so we have here this proximal domain binds in a one-to-one calmodulin. It does not oligomerize, while the distal part of the C-terminus oligomerize, where the LXC is a dimer and LXD is a tetramer. Then we crystallize the coil-coil LXD. It's a tetrameric parallel oriented coil-coil structure. The dimension of the coil-coil are about 50 angstrom long, so it's a long coil-coil, with about 9 helical turns and 4.5 heptad. You know that the coil-coil is an heptad repeats, okay? So you have 7 hydrophobic, more or less hydrophobic amino acids, where the A and D amino acids are very hydrophobic amino acids. And you have an external hydrophilic interface, and the internal interface is very hydrophobic, and you have this coil-coil structure. So we have a tetrameric parallel-oriented coil-coil structure, and our crystallographic data suggests a kind of dimer organization, which is not a surprise when we know that already the potassium channel have a kind of dimer biogenesis and organization in terms of the maturation of the channel. Then we try to map on the crystal structure the long QT mutation. And interestingly, the long QT mutation, of course, the KCNQ1 is plenty of naturally occurring long QT mutation. And if you map this long QT mutation onto the LXD, you see that the long QT mutation are located or mapped to the outer polar surface of the network of the coil-coil, okay, and not to the hydrophobic core. That way, these mutations affect, so we analyze, of course, the current. That way, these mutations impact on the, more or less on the density of the current and the trafficking. So we used, again, this cell surface biotinimation assay, and we found that all long QT mutations that map to this LXD coil-coil are affecting the trafficking of the channel. Okay? So LXD is very important for the tetramerization, but also for the trafficking of the channel, the proper trafficking of the channel. And interestingly, if we, and this we analyze by, again, using this very heavy analytical ultracentrifugation, we try to know, to understand whether these long QT mutations in LXD are affecting the tetrameric organization. They do not. So we still have a tetramerization of these long QT mutants, because there are most of these, all of these long QT mutations mapped to the outer surface. Then, recently, and this is the work that we are now preparing, we crystallize LXA and B, so all these parts of the channel, so this domain, so starting from the C-terminus of the S6 segment up to LXB, and we crystallize it in the presence of EGTA, 1 millimolar EGTA, or in the presence of 5 millimolar calcium. Okay? And we got this organization. So calmodulin is bound to this domain in a very interesting way. We have, first of all, this LXA and B which are oriented in an anti-parallel fashion. Secondly, both in the EGTA crystal and the calcium crystal, we have only the N lobe of calmodulin, which is calcium liganded, as you can see here. So we have calcium atoms in the N lobe of calmodulin, which are actually found there, while the C lobe is empty of calcium. The N lobe is contacting the B helix, while the C lobe is contacting the A helix. And to our surprise, the A helix is much longer than what was predicted from the algorithm, the bioinformatic algorithm. So we can model this A and B helix to the general structure. This is one subunit, so, and you can see here. I think I can show it much better with the no, it's okay, it's okay. So here you can see that the A helix that contact the C lobe, the A helix is just the prolongation of the S6 segment. So we have a very long road of this structure that is actually part of the gate. I mean, we have really a long, very long alpha helical structure that forms the gate of the channel. And of course, here you can see that the N lobe is calcium liganded and contact in very interesting manner the B helix. But then things complicated, and again, the crystal structure does not solve everything. In the structure, and we found that one molecule of calmodulin is actually bridging two different subunits in the crystal structure. So here we have the N lobe that contact the B helix of one subunit, while the C lobe is contacting the A helix of another subunit, as if calmodulin was bridging two neighboring subunits. But we know that this is kind of artifact. And this is an artifact that is found very much, this is very often in crystallization procedure, because you are using huge concentration of protein, and we have the problem of what is called domain swapping. Everything is, I mean, in the crystal structure, everything is fine, except that the fact that calmodulin is not bridging two neighboring subunits. Why? Because we have these data of analytical ultracentrifugation that showed that actually one molecule of calmodulin is binding to one C terminus. So we have a one-to-one stoichiometry. Otherwise, if this was the case, that calmodulin actually bridges, very much like the SK channel, bridges two neighboring subunits, we would have expected a much higher weight when we do this kind of analysis, which is a very precise analysis of the molecular mass. Okay? So we believe that actually the structure and the contact are fine. Everything is fine, except that calmodulin is binding to helix A and B of the very same subunit. And yes?
So just a technical question. So in your sedimentation experiment, what's the concentration of it?
I'm sorry?
In your sedimentation experiment, the centrifugation experiment, what is the concentration?
Oh, we are working in range which are comprised between 2 milligram per ml up to 10 milligram per ml. But for crystallization purposes, you can reach something like 50 milligram per ml. So, and then you have this problem of domain swapping. So to solve this issue, we made these are the questions: whether calmodulin is bridging two neighboring subunits or is binding to one to the very same subunit, as shown here, as it is shown here, or shown here. So this is a very important issue. And to solve this problem, we constructed a tetrameric concatenator of the KCN, or the KV7.1 subunit, where we have introduced mutation that affect the binding of calmodulin. So we know that because of the crystal structure, we know exactly what are the domain of interaction between calmodulin and helix A or helix B. And this is for sure the right structure. So we introduced a mutation in helix A in one subunit, and a mutation in helix B in the neighboring subunit, and in alternance. So we have compared this structure with this structure where we are mutating in the very same subunit, helix A and B. And then we analyze the current. We also analyze the calmodulin binding to this channel. And actually we could find that when we have this type of mutation, we knock down totally the current. Okay, we have no current. This is shown here. This is the IV, okay, of the very little current. We have knocked down something like more than 90% of the current. While when we have this configuration, we still have room for binding calmodulin to intact subunit here, 1 and 2, and we still have current. And this is what you see here. So we have this concatenator, for example, here in the presence of EWA, of the beta subunit, and we still have current, and the current are functional, and we suspect that actually the way by which calmodulin interact with helix A and B is within the same subunit, okay, not bridging two different subunits. The similarity with the SK channel is that, like in SK channel, the calmodulin has the N lobe, which is liganded with calcium only in the N lobe and not in the C lobe. So these are very similar structures that are found for the SK channel. Then we analyzed the interaction. So this was the kind of oligomeric state of the Kv7.1 C terminus. Then we analyzed the interaction between the C terminus of the beta subunit and the C terminus of the alpha subunit. So to do that, we did a lot of construction and purification. We first checked the interaction, the potential interaction of the KCNE1 C terminus with the Kv7.1 alpha subunit, first by co-immunoprecipitation, and this shows the co-immunoprecipitation of the two proteins, the two C termini of the two proteins. Then in order to go further, we prepared and expressed the two C termini of the alpha and the beta subunit. We expressed it in bacteria, so we expressed it recombinantly. We purified by affinity chromatography and size exclusion chromatography. Very a lot of work. So we co-purified and co-elute the two proteins as a ternary complex. As you can see here, this is the elution of the beta subunit alone, but when you co-express, everything comes together in size exclusion chromatography, where you have a complex of the C terminus of the alpha subunit, calmodulin. Calmodulin is in any way necessary to get a soluble protein, and the C terminus of the beta subunit. So you have a ternary complex formed by these three proteins. Then we did a lot of construction where our question was at which domain the C terminus of the beta subunit is interacting with the C terminus of the alpha subunit. And to cut the story short, and we made a lot of construction, we found that the C terminus of the beta subunit is interacting with the coil-coil helix C. If you remember, the helix C is a domain which is it has a kind of dimerization function. Okay, it's a dimer. So the beta subunit, the C terminus of the beta subunit, is interacting with the coil-coil helix C. So, and then we wanted to narrow down the kind of interaction. We wanted to know which part of the C terminus of the beta subunit is interacting with the coil-coil helix C of the alpha subunit. And we found that if you remove this very distal part of the C terminus, you lose the interaction. These are purified protein and pull down. So we do a pull down in order to analyze the interaction between the two proteins. And as it is shown here, when you remove the distal part of the C terminus of the beta subunit, you lose the interaction with the coil-coil helix C of the alpha segment. On the other hand, if you remove this part, the proximal part of the C-terminus, you increase the binding of this part to the coil-coil helix C. Okay? And this recalled us a finding that was found by the group of Sanders in Vanderbilt, and they measured, they analyzed the NMR spectra of the KCNE1 protein, and they found that actually this part of the KCNE1 C-terminus is a very disordered one. So we believe that the C-terminus, and especially the distal part of the C-terminus of the beta subunit, behave as an intrinsically disordered protein. And in intrinsically disordered protein, when it finds the partner to bind with, it depends very much on the flexibility of the tail. When the tail is trying to catch the target, if you get a more rigid tail, then the binding affinity is increasing, and you increase the binding. And this is what you see here. When we remove this part, we get a much stronger binding of this distal part of the C-terminus, of the beta subunit on coil-coil helix C. Interestingly enough, there are long QT mutation located here in this distal part. We have a mild long QT mutation. This is the valine 109 into isoleucine, and we have a strong severe mutation, proline 127 to threonine. Okay, and then we analyze this long QT mutation located in the C-terminus of the beta subunit, both functionally and also in pull-down interaction with coil-coil helix. What we found is that for the mild long QT mutation, valine 109, we have rather the same current amplitude. But for the proline 127T, we have a significant lower channel density. It's not a very strong decrease, but we have consistently something like 30-35% decrease in the current density. This is shown here. No effect on the gating, the same activation curve. And interestingly enough, if you analyze this long QT mutation, this proline actually has a much marked decrease binding to coil-coil helix C of the alpha subunit. This is the wild type. This is the mild mutation V109, which does not actually display a change in the binding to coil-coil helix C. But this long QT mutation has a very marked decrease ability to bind coil-coil helix C of the alpha subunit. You can get the same picture when you remove this proximal part, because you have an increased signal. When you remove this proximal part, you have the same feature, except that the signal is even much stronger. So this is the wild type, this is the V109, and this is this long QT mutation, proline 127T. So coil-coil helix C is very important for interacting with the beta subunit. It's a domain that is important for a proper channel trafficking. If you remove coil-coil helix C from the channel, you lose the current, and everything is stuck in the ER. The channel does not get to the plasma membrane. Then we analyze other mutations. Just go back to so mutations. There are long QT mutation in helix C. So we analyze on the side of the alpha subunit the long QT mutation of the coil-coil helix C, and we found that most of these mutations, except the R55H, are affecting the current density, so they decrease the current density. These are the data, as you can see here. This is the H mutation, which is not affected. We don't know why, but here we have much less current density, also for this mutant, and we have for this mutant also a shift to the right in the activation curve. This is right for the 557, 555C, and all these mutations. All of them are located in the coil-coil helix C. then, and this is the last part of the results, we wanted to analyze. Of course, all these are ongoing. These are not yet published data, and we are now trying to crystallize the C terminus of the beta subunit together with the coil-coil elixir and even to the whole C terminus of the Kv7.2. So then we try to analyze what kind of motion are undergoing the two subunits upon gating. So in order to do so, we fused to the C termini of these two subunits fluorophore, a very classical way, ECFP to the C terminus of the Kv7.1 alpha subunit, and EYFP to the C terminus of the beta subunit. And then we did FRET experiment, but functional FRET experiment. So we did spectral acquisition, and coupled to this spectral acquisition, we recorded the currents. Okay, so we analyzed the channel in the closed state by clamping the channel or the cell at minus 80 millivolt, and then we applied depolarization in order to open the channel, and at the same time we recorded the FRET. So first of all, from the data we show that in the channel closed state, the C termini and the C termini of the alpha subunit, as you can see here, of two neighboring subunits, are in close proximity. We found also that the N and C termini of the neighboring alpha subunit are also in close proximity. As you can see here, these are the fluorophore that are fused to the N terminus and to the C terminus of the Kv7.1 alpha subunit. Then we wanted to know what is the status of the C terminus of the alpha and the beta subunit. So again, we fused the ECFP to the C terminus of the alpha subunit and the YFP to the C terminus of the beta subunit. And as you can see in the FRET, we have found that in the closed state, the two C termini of the alpha and the beta subunit are in close proximity, and this is in line with electrophysiological experiment, but also with the biochemical experiment. We found that actually, for example, the distal part of the beta subunit is in close proximity to the coil-coil elixir, for example. Then we wanted to analyze what is the kind of FRET that we are getting when we open the channel by applying depolarization. So we did the simultaneous recording of the current. So this is the current that we get, and at the same time we acquired the FRET spectral change by analyzing the spectral images at a rate of one spectral image every half a second, and then we could see that on top of the static FRET that we get in the closed state, we have a change in the dynamic FRET. So this is the change of FRET, the relative FRET that we get when we apply depolarization, as if we get a closer proximity of the two C termini, which are reporting, of course, the gated motion of the channel. So this is what we get when we apply depolarization, when we open the channel. Interestingly enough, and this was a kind of proof of the reported motion, we analyzed the same dynamic FRET with one long QT mutation located in the C terminus of the beta subunit, the D76N. This is a very well-known long QT mutation in the beta subunit. So when you do exactly the same experiment with this long QT mutation in the beta subunit, you lose, of course, the current. You have to depolarize to very high depolarizing potential in order to get a very tiny current. So you have a kind of loss of function of this current, and you don't get this FRET change. So you knock down the dynamic FRET that you are getting when you open the channel, the wild type channel. Okay. So apparently, during channel gating, during depolarization, the beta subunit is not a kind of static subunit. It has some kind of motion. For example, other groups have claimed that maybe there is a kind of rotation of the beta subunit and motion of this beta subunit during gating. So we found that using this dynamic FRET experiment, we found that the C termini of both subunits are experiencing molecular motion which are disrupted with this long QT mutation D76N, which is located in the C-terminus of the beta subunit. So to conclude, in trying to put everything together with the kind of structural data, the partial structural data that we have, and the biochemical experiment and the functional experiment that we have this long C-terminus of the alpha subunit, which is built up of several modules. So we have the first module, the first proximal module comprises helix A and B, which bind calmodulin, and the binding of calmodulin is a 1-to-1 ratio, and our biochemical experiments are really clear about that. And they do not promote oligomerization, so this is a 1-to-1 ratio. And we found that calmodulin is very important for folding, trafficking, and also channel gating, because we have this kind of macroscopic inactivation and right shift in the activation curve. We have then this coil-coil helix C, which encodes a dimerization function. This coil-coil helix C is very important for interacting with the tip, the very distal domain of the C-terminus of the beta subunit. We have the helix D, which has a tetramerization function, and this is a very, very important subunit. When you remove helix D, you don't have any kind of current, you don't have any assembly of the channel. This is the equivalent of the T1 tetramerization domain of Shaker channel. Interestingly, mutation in this helix D are also affecting channel trafficking. So these two coil-coil domain, helix C and D, have kind of very important function, not only for assembly, but also for trafficking. Okay? And finally, I would like to thank the people who did the work. So my student, Yoni Haitin, is now in postdoc in Bill Zagota lab. Inbal Bental, Meidan Vir, Asher Peretz, Laura Shamgar. We are collaborating, this is a long-standing collaboration with Olaf Pronk in Hamburg, and Joel Hirsch is a crystallizer, so he has done the crystallization work together with Dana Shaham and Reuven Wiener and the funding agency. Thank you very much.
Thank you very much, Bernard. It's truly a lot of work, as you said. So I don't know, questions to Dr. Smriti there.
Looking at the recent paper in Biochemical Society, where they showed that the C-terminus of E1 binds to helix A. Do you have any comments on that?
Yeah, I don't know. Frankly, the kind of biochemistry that was done there is, they are not really doing a kind of purification of the purification procedure is very important, because sometimes you have a lot of data like this which are published even in Neuron or in JBC or other. So you take a protein, you express it in bacteria, and then you don't care about the purification, so you don't care whether they are aggregates, and these are very important properties. So I don't know. I cannot comment on that. I don't know.
You showed that when you delete the distal part of KCNE1, you see a decrease in current that corresponds with loss of binding of CAM. What about when you do the proximal and you increase binding of CAM? Were you able to see a functional change?
When you increase the amount of calmodulin bound to the helix A and B, that's what you
You showed that when you delete the proximal C-terminus of KCNE1,
yes.
you actually increase the affinity, or increase the CAM binding.
No, it's not the increase of CAM binding. This is the increase of the C-terminus of the beta subunit, the helix C.
I'm sorry.
It's
right.
not an increase of the calmodulin binding. No.
Excuse me. That's
There are some interesting features, because in some mutation, the beta subunit can, in a way, rescue the binding of calmodulin. So, and we don't know how.
Did you see the opposite phenotype in the current, though, as opposed to when you deleted the distal terminus?
No. We don't increase the current, no, because there are also gating problems. When you remove this proximal part of the C-terminus of E1, you will disrupt also some gating process there.
I'm sorry. Did you see? I may have missed it. Did you show the data that you delete the very C terminus of KCE1 and you still see the expression of the channel?
You mean this data? Yeah. You are talking about this deletion or this deletion?
C terminus deletion.
The C terminus deletion.
Yeah, you see the interaction that is gone.
We do see a kind of 30% decrease in the current.
30% decrease in current.
Yeah.
But you still see current.
Oh yeah, we do see current.
How long is that C terminus?
This stretch is about 20 amino acids.
And this is the 20 amino acid that is important for the binding. So did you do different?
Important for the binding, yeah. For the binding to elixir.
Yeah, but did you do serious deletion to just define what the bond
Yeah,
is?
if you increase the extent of the deletion, then you lose much more current. Okay, but if you keep this domain, I mean about 20 amino acid, you do see a decrease, but a moderate decrease. This is not a knockdown.
Modular decrease of the current.
We have to think about the point, the domain of contact of the beta subunit with the alpha subunit. Elixir is not the only domain of contact.
Right.
So KCNE1 is still interacting with the transmembrane segment. It's probably interacting with the also extracellular domain. So we have a lot of contact between the two subunits.
Sure.
But this contact was lost.
So
And
this
still
is-
you get some decrease in the current, which are probably, and these are our preliminary data, that probably we are affecting the trafficking. So you have less channels with traffic to the membrane. But this is not an all or none decrease. No.
I see.
Kind
So
of moderate.
this is a moderate decrease in current, but it's a complete decrease, complete gone of the interaction.
Yeah, that's right.
Okay.
That's right. Yes.
So I'm not familiar with this field at all, but it seems like a very elegant and complex mechanism. I wonder if you have any insight into how this multi-protein complex and function evolved. You mentioned Shaker.
Yes.
Is this related to Shaker? Or?
Yeah, that's very interesting to compare, for example, this channel family assembly and gating process with respect to the shaker type. For example, if you look at the shaker type, you have actually assembly. Okay, in the shaker type, the assembly domain is in the N terminus. The N terminus is also very important for the gating. It modulates the gating of the shaker channel. The N terminus is located upstream the voltage sensor. So in this family of channel, the assembly domain is in the C terminus, and this module is located downstream the voltage sensor. So the kind of interaction is different. You have very different types of interaction.
So does that mean that your gene did not evolve from Shaker, it evolved from something else? And I wonder how, why?
I think it's different types of, diversity of assembly and diversity of interaction. I mean, these are both are quite related. I mean, there are a lot of homology between these two channels. But the mode of assembly is different, and this has implication in the behavior, both in the gating. For example, if you do some mutation in the shaker in this region, you do not very much affect the gating of the channel, not really. But in this family of channel, you do affect, because you are really you are here affecting the gating module, which is important. It binds calmodulin. It's probably very important for folding properly this part of the channel, and this region is really located immediately downstream the S6 segment, so near the gate. So it's different. So the implications are really different in terms of function. So
I guess I'm trying to figure out why did this happen? Like, what
you have actually other types of channel, the trip channel. I don't know. So trip channels are cation channels, are very important. Many functions. They have also this kind of assembly in the C terminus. They have this coil structure. So you have family of channels that assemble via the C terminus. You have family of channels that assemble via the N terminus, but again, the location, you have to think about in the ER when the nascent polypeptide is assembled. So the implications are very different. When you have to oligomerize this subunit into tetramer, for example, and then the assembly is located at the very beginning of the polypeptide, the way by which it assembles and the way by which the whole gating process is functioning is different when you have oligomerization only at the end of the synthesis of the protein, because the assembly here is in the C terminus. So these are kind of variants in the mode of assembly, and there are differences. I mean, both are voltage gated potassium channel, but the way they assemble is different, and there are functional implications.
Oh,
For example, the shaker does not bind the calmodulin. This family binds calmodulin, so this is not, this is on purpose. There are functional implications. The BK channel. BK channel is also very important. This part, this proximal part of the C channel in BK channel is very, very critical for the gating process. While the BK channel has the voltage sensorized shaker. But if you touch at this gating module, you really disrupt very, very markedly the way by which the channel operates. Yeah.
Is it known what residues or targets for CAM kinase 2 and how many targets there might be on
an
both
important question.
subunits?
We still don't know, but we are working on that. Yeah. Yeah. Apparently, CAM kinase 2 is working on modulating, providing the calcium modulation of the channel.
And do you
We
think
don't
there
know.
are targets on both subunits?
No, we believe that no, it's working on the alpha signal.
Just the alpha?
Yeah. We have the modulation of the alpha. Yeah.
So just this structure biology. So when you saw in your crystal structure, you see the A and the B.
Yeah. This is fine.
Yeah, are coming from different subunits, right?
Yeah, but again, this is a swapping problem.
Right, swapping problem. So in the swapping problem, then how confident are you that if there's no swapping, if it comes from the same subunit, as you suppose in the native channel?
Well,
What is the confirmation of the structure will be similar to with the swapping, or what's your take on that?
we are working on that. It's a big problem. I mean, you have to be very, very careful when you do this kind of crystallization procedure, because we have a kind of a discrepancy. On one hand, we have these biochemical experiments which are very fine. I mean, we know that we have a one-to-one stoichiometry, and we know that calmodulin binds to the same subunit. So with these crystals, we believe that the anti-parallel organization of helix A and B is fine. This is something that makes sense, and there is no problem with that. The contacts are fine, but the two different subunits is a kind of very frequent problem when you talk with the crystallizer. I mean, this is this happens very often. When you increase the concentration in order to crystallize the protein, you have some very, very often this swapping problem. So we work on that to try to solve the issue. So that's why we are very careful.
Okay, well, thank you again for